IDA has committed to advocating H2O minus CO2 solutions to reduce the CO2 footprint in desalination by incorporating renewable energy to power both large and small-scale systems. Collaborations like today's are in line with IDA's goals, which are worldwide development and promotion of the appropriate use of desalination and water reuse technologies, coupled with efficient use of energy for water. We encourage research and development in this field with the overall aim to ensure reuse and desalination are part of the circular water economy and efforts to diversify water supply sources to enhance long-term water security and climate change adaptation, essentially leading to the United Nations Sustainable Development Goal number 6, Water for All. Today's event brings together the round 2 quarterfinalist prize competitors and includes a networking session, so those of you on the line may discuss collaboration opportunities with the teams to move forward to a fully operational prototype. We proudly endorse the DOE and NREL Solar Desalination Prize, and we congratulate all 12 teams involved in today's teaming webinar. To tell you more about the Solar Desalination Prize, I'd like to pass the floor over to Danny Zimny-Schmidt, who is the NREL Prize Administrator. Daniel, the floor is yours.
Hey, Danny, you'll need to turn on your mic and camera.
As Shannon mentioned, I'm Danny Zimny-Schmidt. I work at the National Renewable Energy Lab as the prize administrator for the Solar Desalination Prize. I manage much of the day-to-day responsibilities for running this prize. We're very excited to partner with the International Desalination Association for the event today and bring in a broader audience for all of our quarterfinalist prize teams. In addition to IDA's contacts, we have also invited some water testing facilities in the United States and the Clean Energy Business Network to connect with teams today as potential partners as they move into the teaming phase of this prize. The Solar Desalination Prize is a competition designed to accelerate the development of systems that use low-cost solar thermal energy to produce clean water from very high salinity water, such as water produced from oil and gas extractions. The clean water produced can be used for municipal, agricultural, industrial applications, depending on the target markets identified by each team. Our 12 winning teams today from the innovation phase of the prize will each present their innovative concepts today. And these 12 teams were chosen as winners out of initial field out of close to 100 submissions. So we really believe in the potential for their innovations, and we would like to see them all succeed. Many of these teams are looking for additional partners and expertise as they move on into the next phase of this prize. And so we encourage all attendees today to speak with the teams during the networking session that will follow their presentations. Each team has been assigned a table once we return to the REMO event. And we ask that each team leave one person at their assigned table so that other attendees interested in talking with their team will be able to find them there. And if you're having any issues with your audio or other technical aspects today, please message Harrison Dreves in the chat box. And you can find the chat box by expanding the blue arrow on the right side of your screen. I'd now like to give the floor over to Shane Powers from the Department of Energy, who will share a few more details about the Solar Desalination Prize.
My name is Shane Powers. I'm here today representing the Department of Energy. First I want to congratulate you all for being selected to compete as part of the teaming process of this contest. I think we're all excited about your innovations, and we're looking forward to hearing more about them. I want to encourage everybody to use this opportunity to really collaborate and network. This is one of the few chances you're going to get to find the missing elements that's needed as part of your team. Critical part of this prize is to show us at the DOE and NREL that you have the personnel and the skills as part of your team to execute the innovation that you've won the first round based on. This is about teaming. So we want to see that you have all the different elements necessary to take this innovation and bridge the valley of death, if you will, advance level from a very low level up to a very high level, culminating in the construction of a prototype unit. I want to, I guess, the same question all the time. What do we need to do? The point of this contest is not for you to win the contest. The point of this contest is to help you and your team achieve your goals, whatever that might be, presumably to launch a product or such that it makes an impact into the marketplace compared to the competing technologies that are out there. So it's really up to you to define what that market is and what elements you need to bring together and sell to us the concept and the vision that you have for your innovation. And we're here to help you do that. So use this opportunity to collaborate. I'll be with Danny at the administrator table as part of the table sessions if you need any questions. But thank you very much. Danny?
Okay, well, thank you, Daniel, and thank you, Shane. And thank you again for the collaboration with IDA. It's now my pleasure to introduce to everyone our keynote speaker, a person very well versed in the water sector, a global thinker, and actively working to change the future of water as it relates to both energy and production. Mr. Gavin van Tonder is the water sector head at Gyeong, which is a dynamic new project in Saudi Arabia. Gyeong is working to change the water future by minimizing water cost, eradicating waste, and preventing pollution. This means recycling 100% of wastewater, a net zero footprint, renewable energy, and seawater mining. He is leading the development and innovation hub and center of excellence designed to attract leading related industry expertise and research. The center aims to become a global leader in water technology. Gavin, thank you for joining us today. The floor is yours.
Thank you very much for the kind introduction, Shannon. Very much appreciated, and it's a pleasure to be here with all of you. I'm assuming I just share my screen now.
Open up now. Give it 1 second.
Yeah. Are you going to do something here, Harrison?
Yeah, can you try again, Gavin? It's not coming up. You might just need to try it again.
No problem.
All right, loading now. Yeah, looks good. You're all set.
Thank you very much. It's a pleasure to be here with all of you. I guess many people won't know what NEOM is. So we did a little map for you here. So it's located in the northwest of Saudi Arabia. It's on the border of Jordan above it. To the north, to the west is the Aqaba Gulf. Across the Gulf is Egypt. And that's the Suez Canal that you can see heading up towards the left where you see the little NEOM emblem. So this is an international project with a range of international people. I think the second biggest international community we have here is actually Americans. By the way, I came here from Austin, Texas, where I was running a technology company before I arrived here. That gives you an idea where it is. We term NEOM as an accelerator of human progress. So it's an economic engine for this region of the world. It's a way to wean Saudi Arabia and the Gulf region off of oil. It's a powerful approach to environmental conservation. So what we aim to do here is really focus on the environment. We're also creating a living laboratory, which the aim for the laboratory is to be able to test out all new technologies. For those of you that are in the solar field, you will know that this is probably the best solar footprint in the world and gives the best performance. When I walk out of my accommodation in the morning, if I see a cloud, I'm surprised. That's kind of the kind of solar energy we have here. It's an international community. We have, I cannot remember the exact number, something like 60 different nationalities here. 70% of them are international. And as I said, I think the second biggest was from America. So the whole focus for NEOM is to focus around livability. So we want to have a region. So the region's about the size of Belgium. Not sure what state I would use in the USA. Certainly not the size of Texas, but about the size of Belgium. So we aim to redefine livability. So the big focus here is the harmony with nature. We also aim to redefine businesses. We're going to use international standards here. And we're looking for sustainable innovation and building out the region in a sustainable manner here, and redefining how we look at conservation now. It doesn't say so on the slides, but the way I look at it is that we are not looking at only sustainability in NEOM. We're looking at how we can enhance and regenerate, rewild, enhance and regenerate. So we're looking to protect what we have today. In fact, in this region, we have some of the best reefs in the world. They are unexplored because it's been a really protected area and out of the world's sight for a long time. And the reefs are really phenomenal and some of the best diving in the world here. So we have to protect this environment. The land is also quite well protected. Of course, it hasn't really been looked after, but that means that there's not much there. So we're actually going to reimagine here the relationship between people and nature, and that's the intent. So from a water perspective, so just to put it in context, there are 16 different sectors. Water is just one of them. Of course, we have energy, tourism, sport, and a bunch of others, which you can see on the website. But we want to do something that has never been done before here. And we want to change the way people look at water. So we want to create a global reference for water on improving water performance sustainably. So we are going to build off the implementation of a world-class, smart and connected infrastructure here and focus on future innovation and technology. As Shannon said, we are building out an innovation hub here. Apart from the infrastructure, we're building out an innovation hub here. We already have innovation that I will talk to in a minute around solar dome technologies. And we are looking at specific desalination technologies. And when I say we are focused on the environment here, all of our desalination will be done with renewable energy. So we will have no fossil fuel energy inside NEOM for the whole region. We will, of course, use special seawater intakes to protect the environment, and there will be no liquid discharge out of our desalination facility. And we look to then process those brines to produce products, chemicals, and minerals in a green manner, because everything will be with renewable energy. Our biggest focus is not to try, but make sure that we have the lowest water losses in the network possible. Of course, we're always going to get losses, but keeping that down to a minimum is what our focus is on. The lower our losses, the smaller our desalination plants, the smaller our infrastructure, and the less energy we need to pump water around the whole region. And then, of course, as Shannon said, 100% reuse of wastewater that we will recycle back into the system. So no liquid discharge. We will also protect the reefs from runoff. So there will be no urban runoff into the reefs from stormwater runoff. So we have let's say a vast strategy, and I don't have enough time to go through everything, but we will be a global leader in renewable powered desalination and zero liquid discharge. And I'll only talk about that today. So, as we know, desalination started off with MSF and MED, and if you look at the electrical and the thermal energy demand that came out of that historically, it was quite large, around 50% of the total desalination costs. And then with the advent of reverse osmosis about 15 years ago, we started to see a dramatic decrease in the amount of energy that was utilized. And zero thermal energy in that. And then as we started to go to what we're looking at from you people is the direct renewable aspect. Can we go to direct solar or direct renewable energy and get rid of thermal and electric energy completely? And that's what we're looking at in NEOM, and that's what we're willing to test out in NEOM in our innovation hub. If we also look at the range of levelized cost of electricity, we compare our nuclear, coal, and gas. And then what we did was we looked at the wind and the PV and the CSP, and there are some lower levelized costs that's occurring. In the region, in the Gulf region, you can see Saudi Arabia actually has probably the lowest levelized cost for wind and PV, and that's just because it's quite windy down there. And we have a huge amount of sun here. But frankly, what we want to get to is the direct renewable, where the levelized cost of electricity should be virtually zero. So that's the direction that we're going in. Of course, we've looked at what has happened in the world and how the world has started to move towards renewable energy, whether that be solar or wind. And we've seen the dramatic effect that has had on desalination costs. So, conventional power at $0.12 per kilowatt hour moves across to renewable energy at $0.05 per kilowatt hour. And in fact, there are areas now that we get it down to less than $0.03 per kilowatt hour in NEOM. That means our desalination costs have dropped, by 30% in the last years, and that value is coming down dramatically. Of course, there are some countries that claim that they have renewable energy desalination, but let's face facts, it's few and far between today. Also, when we look at it, we're looking at grid connected compared to integrated locally solar, and we don't really see that as what we want to do in the future. We're not looking to offset with carbon credits, but we are looking to have a fully renewable system. But that's only for phase one because that technology is available. What we're looking for here is technology that can take us to the next level in the next 5 years and where we use renewable energy directly. So we looked at the energy efficiency and how we would use different energy efficiency. Right, of course, we're right next to the sea, so we can also have wave power, and there's claims that wave power can have up to 50% energy efficiency. Wind turbine between 30 and 40% with a peak at 50% in our region. Pumped hydropower is obviously very interesting for us because in our region we have mountains that are around 8,000 feet high. And we could get up to 87% energy efficiency using hydropower. And then, of course, solar PV panels, the energy efficiency range for us is heading up towards the 25%. And interestingly, we're also looking at undersea desalination using reverse osmosis, where that utilizes actually the water depth for the energy. And here, it's still a fairly new technology. We have to look at how the efficiency is going to be in that technology. So what is interesting here, and I don't know if this is covering up anything, if you look at, again, the conventional power and the renewable energy, what we're heading towards is solar energy, which could be virtually $0 per kilowatt hour if we can do it correctly. You will notice I put 0.01 because we're still going to need some things for pumps, etc., to move fluid around. But the focus here should be on the capex reduction, because as you can see, if we can get down to very low dollar values per meter cubed of desalination, we're going to get down to a big focus on capex and how we can reduce it. And one of the projects that we are working on. So the key issues to solve, actually, and from our experience of working on direct solar desalination at the moment, are maintenance, capital cost, the efficiency and the performance, and the lifetime of the asset. When we look at putting these remote devices into the field, generally you don't have people there that can fix the technology. You don't have people there that can drive the technology. If you're looking at putting something in Africa or on the coast, where people don't have water today, you have to have a strong focus on maintenance-free systems. So what we have worked on already in NEOM is what we call the solar dome. It's a technology that came out of Cranfield University, a company called Solar Water. And we've been through a few iterations here because essentially it came off the research bench. So what the idea was that you would have an open flow tube which brings in water into the desalinator and as it brings in the water, it heats up the water at the same time. And then the water evaporates inside this solar dome with a highly conductive steel frame. And then pressurized steam is produced through this. It then condenses and comes out as fresh water. And then you can actually then get the high recoveries out of this, and you can decide what sort of brine you're going to pull out and what the concentration of the brine will be. If you can get that right, of course, that helps us because we're not going to put the brine back into the sea. So the higher we can concentrate the brine, the less energy we need to process the brine afterwards. So this was designed with mirrors around it that focused on the dome, and then the dome heated up. And I can tell you, it was a very tough one to get through, and the initial concept has changed from now. I'm not at liberty to explain the new concept today, but just to show you that we are working on this and we are testing this out, and we have an innovation hub where we do test these technologies out inside NEOM. One of the other things we looked at was actually a project with a company called 1366 Technologies and MIT, why don't we, because we have these huge mountains that look exactly like you see on the screen, why don't we use a solar array and wind, pump the seawater up into a dam, and then use the pressure from the water to desalinate. And it gives you obviously all the water and the pressure that you need at the same time to desalinate. You use renewable energy only to pump it up and fill up the dam. So a very unique concept and something that still interests us a lot today. Of course, to justify that, you're talking about $5 billion to develop something like this. So you really need a strong population that would take the water from this in order to do that. We just don't have that strong population. We're just a brand new region developing out. We only have 30,000 people here today. So, it is something that we're looking at. And it brings me to let's say, the point here that is essential for our planet going forward. We've all, let's say, certainly in the GCC area and in Saudi Arabia, there is no water. It's the biggest country with no surface water. And a population of over 30 million people. So we rely a lot on desalination here, more than 50%. But across the world, we see this is happening everywhere. Egypt putting in 29 desalination plants in the next 5 years. Jordan running out of water. Iran having major water issues. So even Australia putting in a desalination mainly because of drought resistance. So achieving low-cost desalination while protecting the environment is our highest priority. We have a strong focus in NEOM about making sure we don't put the brine back into the sea. So what we do with the brine, doesn't matter what the technology is that we use, what we do with the brine is also extremely important in how we protect the environment. The majority of our costs are actually in delivering the fresh water. It's not in the desalination cost itself. It's actually delivery that from the desalination facility to where it needs to go. So a focus on decentralized small systems that don't affect the environment is really key for us. A lot of that feeds into the technologies that you will probably present to us today. We believe the potential for direct solar desalination is enormous. We are looking at trying to have a desalination facility that requires zero energy and can be standalone and used anywhere in the world. What we have found is that the solution appears to be a hybrid system that takes advantage of all the technologies and the renewable energy available, be that the reverse osmosis mixed with evaporation, or be that hydropower mixed with reverse osmosis. That is what we have seen today. And I'm very interested to see what you're all going to present today. And I'm available here. And from a NEOM perspective, we are very interested to invest in technologies. We're already investing in technologies in a few universities that are building out systems for us. And as I said, we've already invested in the solar dome technologies. So we are very interested, not just for NEOM, but from a global basis, to look at what technologies you have available. And we have funding to be able to invest in those. So that's it for me, Shannon. I don't know.
Okay, well, thank you, Gavin. That was an excellent presentation. I think everybody must have been thrilled, those who don't know about NEOM and what they're doing, what Gavin is leading in innovation in the Kingdom of Saudi Arabia. It's really dynamic and so interesting to watch how you're developing this and implementing all these programs. So thank you so much for joining us today. I think it was a great contribution to our webinar. And we'll move now into our next part of the program, which is where we have challenged the 12 team captains, the quarterfinalists, to present their project in 4 minutes. Now that's a big challenge, and we thank all of our captains on the line today for taking this on. We know it's not easy. For those of you who just joined, I'd like to note that once the captains are finished with their presentations, we will move into a networking session, and there will be different rooms you can join based on the project you might be interested in. So moving forward, the first team is Arctic Solar, focused on engineered solar thermal osmosis, and they are from Florida. Captain William Guinea, we welcome you to start your pitch.
Thank you very much. You can see my screen.
Your screen perfectly. Yeah.
Okay. I'm William Guiney, Bill to my friends. I'm the co-founder of Arctic Solar Inc. in Jacksonville, Florida. We did submit a proposal to the Desalination Prize, and we're advanced, and we're very grateful for that. We are a small team right now. Georgia Tech University and Lawrence Berkeley National Lab are our partners, and Porphyra is the manufacturer of the polymer membrane utilized for the forward osmosis technology. Our system is very simple. It uses a membrane that has the feed water on one side and the smart solvents on the other side. Those smart solvents attract the water, pull it in. It is then going to a vessel that will actually be heated by the solar energy, which will separate the fresh water from the smart solvents, so we can regenerate the solvents back to the next round. So it is a very simple process, and requires a fairly low amount of energy that is produced by our XCPC collector. Our goals are to optimize the water flux and have high recovery. We've been somewhere around 60% now. We're looking to improve that. We need to integrate a heat exchanger with a high heat transfer efficiency for either single or multiple fluid passes. We need, because we're going from a ambient temperature to a higher temperature, to be able to separate the solvents from the water. So we're looking for a very good, high quality, efficient heat transfer and heat exchanger. We also have to look at the potential for desalinating 100 cubic meters either in an 8, 12, 16, or 24-hour operation, which means we've got to evaluate the solar gain and the thermal energy storage and what makes the most sense for us to either expand our thermal storage or expand the solar array to be able to meet the goals of the program. So we also need to optimize the delta T across the solar collector, potentially utilizing a series design of piping to be able to increase the temperature coming off of the solar array. And because our performance curve is fairly flat, we can go out to higher temperatures and still maintain high efficiency. So we also need to determine what the life cycle is of those thermal responsive solvents to be able to see how long they're going to last, how many times we can recycle them. Our action items are both now and what we will do in the next phase if we're fortunate enough to advance. So we've got to identify right now the heat exchanger that we want to utilize for the process. We need to identify our thermal energy storage partner and obviously, like everyone, identify a potential site as a team member. And so we'll work with the American-made network to assist us in these tasks and these action items. So we're going to be looking for NREL or others within the CSP group to help us validate the performance of the solar system at the test site, evaluate different thermal energy options, both in the US and in Europe.
Okay, Bill, that's wrap up in the next 30 seconds.
Okay, and so we'll look at the permitting issues. So that's it, and I thank you very much.
Thank you, Bill. That was a great presentation, and you were just about right on time. We appreciate that. I'm going to move next to our next team captain, is Aaron Baskerville Bridges. He is with AeroShield, transparent aerogels to improve solar thermal, located in Cambridge, Massachusetts. Aaron, the floor is yours.
All right, can everyone hear me? So we're good to go. All right, so hello everyone, my name is Aaron Baskerville Bridges, and it's my pleasure to introduce AeroShield, where our super insulating materials are providing a step change in solar thermal performance. One of the core challenges highlighted in the Solar Desalination Prize's application process was reducing the levelized cost of heat. You know, thermal energy helps drive a lot of the desalination systems that you're going to hear about today. But given the finite amount of energy per square foot of sunlight, capturing that energy efficiently is crucial. AeroShield's material, when applied to a solar thermal system, can improve performance by up to 30%. So how does it work? How are we doing that? Well, let's start with the working principle of solar thermal, because it's quite simple. An object left in the sun will get hot, but as that object heats up, you get thermal losses that hurt your efficiency. At the collector surface, what you need is a material that allows light to pass, but no thermal energy to escape. So what you need is transparent insulation. AeroShield makes super insulating silica aerogels to insulate the aperture of concentrated and unconcentrated solar thermal receivers. For a long time, NASA has been using aerogels on spacecraft because they're some of the most insulating materials ever created. They're super light, they're stable at high temperatures, but for the first time ever, AeroShield is making aerogels that are transparent. This material was developed during AeroShield's founder, Dr. Elise Strohbach's PhD at MIT, and a concentrated solar prototype was made as part of an ARPA-E project. And since then, we've spun out of MIT, and we've been prototyping. We were actually a competitor in the American-made Solar Prize, making flat plate collectors. So some of the key benefits that you'll see from a solar thermal system like ours is that we demonstrated in the course of the Solar Prize through a model with Sandia and then the demonstration that we could operate at 120 Celsius at 48% efficiency, reaching up to 60% efficiency at lower temperatures in the 80C range. We're also highly temperature stable. So the linear Fresnel prototype demonstrated at MIT validated performance up to about 300 Celsius. This is our team. So where are we right now? You know, we are a team of 6 located in Hyde Park, Massachusetts, where we're focused on scaling up the manufacturing of this material, building and testing prototypes, and forging collaborations with partners in solar thermal and insulated glass. If any teams in the competition are unfamiliar with kind of the grant landscape or national labs, this is something that we're happy to help other teams with because we come from the academic space, and this is really a space that we know well. So if anything on this page is of interest to other teams, definitely reach out. We are happy to help. Really, our goals from the competition are to collaborate with Solar Desal Prize teams and collaborate with existing facilities. So if you are a Solar Desalination Prize team and you have a solar thermal system, please reach out to us and we can talk about how the aerogel could improve the efficiency of your receiver. We'd be happy to supply aerogels for your project. If you're someone who needs a solar thermal system to work with your membrane or other system, we have a manufacturing partner that we've started working with, and we could design a system for you. If you're an existing facility, the same thing applies. We want to partner with you to see what types of solutions could exist. In terms of expertise asked, we're looking for people who can help us understand the list of and types of receivers used in solar desal today, including their operating temperatures and the levelized cost of heat. Of course, access to testing facilities for solar thermal systems, and then expertise in manufacturing scale-up. Finally, if you're in industry and we'd love to make connections to manufacturers of solar thermal systems for desalination or just in general. Manufacturers of low iron and low reflectivity glass for solar thermal, and then of course end users for solar desalination systems. So thank you very much for attending, and I look forward to meeting with you at the networking session. Feel free to stop by our table or reach out to me. There's a contact information right here.
Aaron, that was an excellent presentation. Thank you. And we'll move on now to our next team captain, which is Captain Brandon Hathaway. He is with Sun Vapor. They're focused on solar cascading evaporation processes, and he is from Pasadena, California. So Brandon, the floor is yours.
Great, thanks, Shannon. So I'm representing the team from Sun Vapor, as was mentioned, and we've got here a listing of our key team members, including Philip Gleckman, our Chief Executive Officer, and Sue Gleckman, our General Manager. I'm Brandon Hathaway, the Director of Engineering, and to give you some background about the company, at Sun Vapor here, we're focused on addressing the water, energy, food nexus with renewable technologies and decarbonizing those hard to decarbonize areas of the energy systems. And so some of the experiences we have that we'd like to highlight include project development of multi-megawatt solar steam facilities that have been used for food or biofuel producers. And that development, beyond the development, we also have gone into engineering, procurement, and construction management for actually producing these solar steam systems. In our portfolio of products, we have a high-performance concentrating solar collector that we manufacture that is automated and is robust and simple, with reliable tracking systems for use that's ideal for industrial process heat applications. And this automated system allows us to deliver low-cost solar steam, and we are pairing that with advanced technology for low-cost thermal energy storage of steam for steam applications, and this is being funded by Department of Energy award. And with that bit of background, we'll jump into what our project is, which builds upon our solar technology, our solar steam technology, and introduces a desalination process that we refer to as SEPTER, or our solar cascading evaporation process to recover effluent. So the cascading aspect of this is what's key, in that the system drives a high temperature process that cascades its waste energy, which is now no longer waste, but useful energy, to a low temperature process. So as shown on the screen here, we have our solar collectors, which are paired with our bullet steam accumulator thermal storage technology to provide high capacity factor steam to downstream processes. And we have at first a high temperature process based on an evaporation style system that is thermally driven, that is robust and can handle highly concentrated brines up to saturation conditions. Now, when driving this process thermally, you produce an excess amount of vapor that normally becomes a problem that needs to be rejected and cooled. But we've turned that into a benefit with our system, where we use that heat to drive a lower temperature based process to actually provide initial concentration of our brines up to the intermediate levels that we then pass on to the falling film evaporator. So this allows us to gain just about a doubling of our output compared to using just an evaporator system alone, and all powered with renewable thermal energy. So the goals of this project are, of course, firstly, to establish what the needs are for given sets of customers out there in the market, and what the requirements are to actually be able to demonstrate this at a pilot scale and have commercial viability long term. This will involve a bit of preliminary R&D, where we'll look at the behavior of membrane distillation systems at the conditions of interest and verify the optimum designs for the evaporator system in such a cascading layout. We'll then follow up with our pilot demonstration and analysis of the demonstration performance to make sure we can reach performance and cost targets. So our big expertise ask here is to look for those who have knowledge in the brine disposal economics and have insight into the markets of interest here. So knowing about typical costs that would be of interest and what economic structures are of use. We're also looking for those with evaporation process technology expertise, including vertical falling film evaporators and the associated chemistry required to operate them and the suppliers of such equipment in the US. And lastly, looking at cooling systems for cooling brine in a final heat rejection step. So if you've got insight into those areas, we'd love to hear from you. And we're also interested in hearing about any potential customers who have some brine disposal needs that we'd be eager to address. So with that, we'll show our contact information and look forward to hearing from anyone who would be interested in partnering up.
Thank you, Brandon. Excellent presentation, right on time. Topic's very interesting. I'm going to move now to our next team, which is our team captain is John Kazaz from Team Trident. They're focused on TSSE, CLD treatment of produced water, coming to us today from Santa Barbara, California. John, the floor is yours.
Wonderful, just making sure you can see my screen. So we are Team Trident. We are a collaboration of multiple entities. First and foremost, our innovation group is backed by Columbia University. Trident Desalination is the commercial wing of the TSSE technology that was developed by Columbia. And our engineering partners are Bechtel. We are also financially supported through New York and Silicon Valley-based venture capitalists. So about TSSE. Team Trident utilizes a multi-stage solvent extraction-based system. I understand that not everyone on the call is probably a chemical engineer, so I'll be relatively quick about this. But essentially what we do is we take a brine stream and combine it with a low-polarity solvent. In the non-aqueous phase, these two objects are immiscible, somewhat like oil and water, but water is actually absorbed by the solvent through natural chemical processes. We can then do one of three different things. At this point, we can either precipitate out selective problematic ionic compounds. We can induce medium liquid discharge, meaning we remove large quantities of the water, but not taking it all the way to zero liquid discharge. Or utilizing more of our solvent compound, we can induce crystallization to achieve zero liquid discharge. Now, we are thermally driven. However, we do not undergo the evaporative phase change of water. This means that we don't actually need a lot of the esoteric or expensive materials that are relatively common in zero liquid discharge or brine concentration technologies, your titaniums and that sort of material. We then can actually induce, just through relatively minor temperature swings, the solvent to release the water in multiple stages. Now, since the boiling point of the solvents is typically well under the boiling point of water, we again have relatively minor energy needs here. In terms of electrical energy, the only thing we make use of is for your pumping system, so fairly de minimis usage. Now, our goals are actually to construct a multi-step continuous use TSSE system that's capable of treating produced water and taking it all the way to zero liquid discharge. We also need to successfully integrate a concentrated solar thermal energy system into the process design framework. We do have a relatively low energy system and can make use of low grade heat. So we have looked into whether or not we want to make use of the solar energy as almost a utility via a heat exchanger, or kind of go direct into the solar integration phase. We're kind of hoping to get better insights into that cost trade-off dynamic. The goal here is obviously to get our price of ZLD all the way down to around $1.70 per cubic meter on the low end, $4 on the high end. And we want to achieve a large solvent recovery rate well above 99.99%, which we have achieved in laboratory settings. Sort of key action items for us is to identify a suitable host site with produced water or similarly high TDS brines. We would like to partner with a solar thermal provider and incorporate the system into our design, finalize some of the key ratios on the commercialization end to go out to companies, and then again, obtain all the necessary permitting for our pilot facility. This is our timeline of events, which you can see we're trying to get connect with most of our partners and get everything wrapped up by the end of December so that we can get our application phase properly designed and get everything permitted and implemented by early February. And our expert asks, we would love mentorship and assistance in the area of concentrated solar thermal. We, again, would like to connect with facility partnership hosts that have access to either produced water or a high salinity brine source. And again, we would really love to connect with domestic manufacturing groups that can kind of bulk produce commercially grade solvents. Our solvent costs are one of our driving OpEx costs. So the lower we can get that, the more aggressively we push towards that DOE $1.50 for zero liquid discharge technology goal. This is me. I'm more than available to connect with anybody and would love to provide deeper insights into what we are doing here. Thank you very much.
Thank you, John. That was a super presentation, and you too were right on time. So moving on to our next captain, I'd like to introduce Alexander Mednick. He is with Physical Sciences, and they are focused on modular, inexpensive solar thermal evaporative desal, located in Andover, Massachusetts. Alexander, the floor is yours.
Thank you very much.
Screen looks good, Alex.
Can you hear me? All right, yeah.
Yep, you look good.
All right, so the MISTA team is from Physical Sciences. This is the PSI team, specifically the individuals, but we're actually representing a larger group of companies, which I haven't shown here, that the goal is to meet all of the requirements of the DOE and be able to make this plant. The MISTA system consists of individual concentrating solar power modules with glass receiver tubes in which salt water is distilled using a multi-stage flash type premise. The idea behind this design is to combine low-cost simplicity of a solar still with the latent heat reclamation and efficiency benefits of multi-stage flash to reduce the part count, the fabrication complexity, and the material costs compared to the traditional high-temperature concentrating solar power equipment. This is possible for the case of multi-stage flash desalination because the maximum temperature is only around 100 degrees C. And this helps reduce corrosion resistance, scaling potential, and the temperature resistance requirements. The goal of the MISTA system is to minimize water cost, levelized water cost of water, rather than maximize efficiency in terms of kilowatts per meter cubed. The increased water production using MSF compared to the solar still is worth the increase in complexity based on our techno-economic analysis. And the overall levelized cost of water is minimized by retaining at least 80% of the performance of existing multi-stage flash plants while creating a solar trough assembly that is simple, cheap, robust, modular, and manufactured using commonly available materials. This makes MISTA an ideal candidate for small installations, off-grid communities, disaster relief, gas and oil produced water, and potentially military uses. Additionally, the modular configuration of the MISTA systems, which consists of a large number of assemblies, or a large number of 20-stage assemblies shown here, means that the technology is applicable to everything from oil well installations down to small trailer-mounted systems for disaster relief response. As maturity increases through development, MISTA will become competitive with reverse osmosis from a cost standpoint, while having the capability of treating much higher TDS feed water. Our primary goal during this phase is to finish assembling our team and then also updating our techno-economic analysis and creating a prototype so that we can have a more complete bill of materials. We're seeking host sites for both the prototype as well as an eventual commercialization partner. We have some of these people slotted into some of these different teaming needs, but we are interested in connecting to other people who may have additional experience in particularly connection to municipalities who may be looking for small scale off the grid desalination, and also treatment of water to prevent scaling. Same general timeline as everyone else on the call. We're going to be anticipating having our team in place by the beginning of next year, and then getting all the partnerships sorted out by beginning of February for the final submission. Same information here. We are the innovator, but we're looking for host sites and would like to partner with manufacturers and commercialization partners. And with that, here's my my contact information, and also that of our commercialization captain, Sean Torres. That's all. Thank you.
Great job, Alex. Thank you. Moving over to our next team captain today, we have Gyeong Zhang from Oakridge National Laboratory, working on solar desalination, modular intensified solar desal technology, coming to us from Oakridge, Tennessee. Gyeong, the floor is yours.
Okay. Okay, everybody's in.
Yes, just put it in presentation mode and you should be all set.
Okay, thanks.
Looks good.
Okay, hello, I'm Gyeong, leading the team of the ORN solar desalinations. Most of us are from the Oakridge National Laboratory. We are all staffs. We have some kind of expertise, and we are all of the chemical engineer and material scientist, and we have interest in about the solar desalination and desalination separations. All others, the member in the Costa Solitos and the James Cleed, we all have some itchy expertise about the separation, desalination, also carbon and carbon composites. And we also have as the working partner, the Well and the Braden, and he's going to help us to this project for the kind of commercialization and the kind of scale up. Okay. For our project, basically initiated with the ordinary solar membrane, which is made by the black graphite foam. The graphite foam is a porous and highly thermal conductive material, which can observe, we tested 96% of solar energy, we can observe that. Then we made the tubular membrane. The inside the channel was coated by the superhydrophobic. So it can hold up the bulk water flow through the channel, and the solar heated up the salt water. It just generates a fresh vapor. That generated fresh vapors pass through the membrane, so we can get the fresh water. And we further developed the membrane coating with the graphene oxide, so it can also dewater from the organic exit. And you can get there's a kind of some desalination. So based on the membrane, we are proposed a project, the MIST, which is the modular intensified solar desalination technology. It can be achieved by using parabolic trough and the concentrated solar power system and the novel tubular membrane, which can be installed in the solar receiver, and it can trap the liquid and allow only vapors produced by salt water, the interior of the membrane wall. So it can be a part of the zero liquid charge. So key concept is that because of the direct heating on the membrane, so we are pursuing the process intensification for the solar desalination. So we are expecting to increase the solar energy efficiency using our system, also reduce the capex cost of. So the project goal here is to demonstrate this cost-effective solar thermal desalination performance using and modular tubular membrane desalination system, kind of simply 90% of salt rejection and the kind of the concentration of the brine water. They can be a part of the zero liquid charge scheme. So in here, we need some expertise. So first, similar to the others, we need a testing site. And also we need looking for some expertise about the solar concentrated solar power. So we did have some of the membrane, but we also need some expertise in there. And then also we also some expertise about the some kind of membrane fabrication of the manufacturing, about the scalable, the microporous coatings. I'm the Zhang. From the Oakridge. Please email me if you have interest about our project and our teams. Thank you.
Wonderful. Thank you, Gyeong. That was an excellent presentation. We appreciate that. Moving on to our next presenter, Team Captain Loon Zhang, who is CEO of Winston Cone Optics. They're focused on portable optics for solar heat, coming to us today from Merced, California. Mr. Loon, are you?
It looks like he's trying to
connect. Okay.
Yeah.
All right.
Excellent.
We
There
can
you
see
go.
it now.
Okay.
All right. My name is Lun. I'm the CEO of Winston Cone Optics, which is founded by Professor Roland Winston, who is sitting by me. We are a team that came off University of California, Merced, where we have done solar thermal research and optics research for the last 10 years together. And we have received multiple awards from DOE, CEC, ARPA-E. So I want to share with you today on a recent solar optics discovery that we made. Let me start with a client who recently approached us. They are an energy efficiency company managing power plants. And he told me that he every year he consumes $300 million of natural gas, and he provides not just electricity, but also steam for the nearby region. And he has been doing some research about generating heat renewably. And one of the things he looked at is the picture on the left, which shows you some tilted stationary collector, such as PV, such as flat plate. And you can notice that there's row-to-row shading in this particular picture. So you have to space this carefully, in general, 1-to-1 ratio. So with this design, you're using 50% of your land area. And this client happens to have his power plant in a crowded area, densely populated. And he's not happy with only 50% of land being usable during the summer season. So he goes to the other design here, which is a Parabolic 12 design on the right. And this one is even worse, is the spacing here is 1-to-2. So only 30% of the land is usable during summer. So he looked at our design and he was extremely excited. And he right away started a conversation about doing a feasibility study of a demonstration project of 20 megawatts or roughly $4 million project work. Let me share with you why he was excited about it. Well, we actually, in the last 1 or 2 years, we discovered a new class of Namgene optics. We call it Namgene optics shadeless for distributed energy. What it does is it uses a low-cost concentrator. We're talking about $10 per square meter of reflective material here. It takes away the shade by flattening out your tilted collector surface onto the roof. So left is a conventional way of doing it. Right is how we do it now. By doing that, you take away the wind load design, or most of the wind load design. You have no moving part whatsoever in order to track the sun. And it's extremely compact. You can achieve 90%, 95% utilization rate of your roof area or your container area if you're using a mobile unit. And we also have a vacuum tube receiver at the middle, which allows us to achieve roughly 330 to 360 degrees Celsius highest temperature. That's roughly 700 Fahrenheit degrees. So how do we do this? Well, we use optics both to track and to tilt in a way. On the left, you can see the ray tracing for the winter season. And on the right is the summer season. Now, we have done ray tracing for everything in between. This thing just works. You set and forget. Don't need to do any additional maintenance. And you can do this for both. You can do it for multiple insulation mounting positions, like the vertical facade on the left, horizontal roof, or any angle in between. What we have really is years and years of solar thermal and optical engineering experience. And we have licensees around the world, including Arctic Solar, who did a presentation on our XCPC product. And we also have the capability to customize our product according to your need. What we need is the market. We need, especially the semi-mobile wastewater processing market. We were approached previously by
Run
the
4 minutes. You have about 30 seconds to wrap up.
Okay, and they were asking for PFAS processing. And if you know anything about PFAS, please find us. And we are looking for desalination technology partner. Thank you for your attention.
Thank you, Loon. Very good presentation. Thank you. We're moving to our next team captain with the same organization. Bennett Woodylar is also with Winston Cone Optics, and the project is on integrated compound parabolic concentrators. He's also coming, of course, from Merced, California. So Bennett, you're welcome to the floor. Please.
Thank you. I apologize. There's somebody on the roof right now trying to fix a leak. So if you hear him, I'm sorry about that. But okay, let's see. Can you guys see this?
Yeah, just bring it up full screen. Looks great.
Okay, so hello everyone. My name is Bennett Woodylar. I'm the CTO of Winston Cone Optics, and we're a startup company out of Merced, California, and we're spinning out some technologies we've developed at the University of California, Merced. And our expertise is in optics, solar thermal, and vacuum tube technologies. And the technology I'll be talking about today was developed with support from the Department of Energy's Solar Energy Technology Office under the CSP Desalination Program. Okay, so the Integrated Compound Parabolic Concentrator, or the ICPC for short, is a non-tracking vacuum tube collector. It incorporates non-imaging optics, an aluminum mini-channel absorber, and vacuum tube technology to efficiently generate 150 degrees Celsius heat from a stationary position. You can kind of see the ray tracing over here, showing all the rays are hitting the absorber. So individual tubes are piped together to make a 20-tube module. Each module weighs about 150 pounds, so it's easily positioned and installed by a two-person team. And modules are rail-mounted, and due to their low wind loading, can use ballast-weighted foundations, which means no ground penetrations. And then modules are piped together using quick connect flexible hosing, and the entire solar field can be installed with no heavy equipment. So as part of our DOE award, we measured the solar to thermal efficiency of a single module up to 140C. So here you can see in the blue is so our optical efficiency testing showing about 70–75% solar to thermal efficiency. We tested up to 140C here in these red dots, and what we're seeing is basically up to 150C, we're above 50% solar to thermal efficiency. We also measured a stagnation temperature of about 300C over here. So the team then scaled up to a 10 kilowatt array shown here at UC Merced. This is 12 20-tube modules installed in 4 banks of 3 modules in series. And so performance of this array was measured while operating at 120 Celsius for several days. The array consistently produced about 10 kilowatts for most of the day and had a solar to thermal efficiency of about 50%. And the average daily efficiency, so of the total incoming solar energy, the fraction of that which was captured and delivered at 120C or above was about 43%. And based on this, we estimate the solar field cost is about $80 per square meter, and with an estimated additional balance of system cost of about $50 per square meter, we estimate the total installed cost of about $130 per square meter. And for an O&M cost of $2.60 per square meter per year, and a fixed charge rate of this from the DOE award, we basically project the levelized cost of heat of about 1.5 cents per kilowatt hour, or 44 cents per therm. So yeah, so now moving forward, our goal is really to identify a cross-functional partner to develop an operational solar thermal desal system at 100 cubic meter per day capacity. Our action items for ourselves are really to just continue development of the ICPC, specifically in de-risking the long-term stability of the hermetic seal through accelerated thermal cycling and exposure testing, And our second major action item is to identify partners. So the deadline of this phase of the contest is February 9th. So we're hoping to meet and collaborate with some people before then so we can submit by then. And we are looking for partners with expertise in thermal desal, thermal energy storage. We're looking for industry host sites and assistance with industry tech to market. And so, yeah, we're very excited to participate in the prize, and we look forward to teaming with you. Thank you.
Nice job, Bennett. Thank you. Good presentation. Moving to our next team captain, we have Brad Hides from Planet A Energy, working on solar heat collector with a built-in storage, and he is coming to us also from California, from Pasadena. Brad, please take over the floor. You're present with your.
Let's see. Share.
Great, we can see you, Brad.
Okay, share screen. Right.
Looks good. Just bring it up full screen.
Yeah. Slideshow. How's that?
Looks great. Take it away.
Okay. All right. So Planet A Energy is a company that provides 24/7 solar heat. So we're a solar collection technology that dumps heat directly into storage. It's sort of intrinsic to our system. Who we are, so we're a system that's a company that's providing solar heat collection equipment. We're very early stage. We've got people that have about nearly 20 years experience in solar thermal in general. This is my third solar startup. Okay, what do we do? So I've shown this here. Our product is this thing in the lower left corner. It looks like a shipping container that goes on an ocean-going vessel. And up here in the upper left, you see the sun cycling daily. We collect this heat, we concentrate it, put it in this box. I'll show you that in a second. And then we deliver the heat to your application where you make water. Here in the lower right corner, we're showing over the course of a week, you can see the temperature going up and down. But you can see we kind of, in this particular simulation, we always keep it pretty much above 500 C. So we provide even reliable heat, even through days of no sun. So here is a picture of what we're doing. Here's our shipping container on the right, and you can see it's got optics on the top that focus sunlight. Inside is a big bed of black sand. This can store days and days of energy, even just in one container. And at up to 600 C easily. There's a block of insulation that goes around it to hold the heat in, and then there's an air gap we can use to extract heat. So we dump solar energy directly into storage. What we do that's unique, and we're looking for partners that want these capabilities, we do 24/7 operation. We can provide high temps up to 600 C in its first generation. We have a rugged system, and we're easily deployed or relocated. And our storage material is this non-toxic, non-flammable black sand. So we want to marry our technology to appropriate equipment. We want to demonstrate capability of 24/7 operation when customers that need it. And ideally, we'd have a site where we demonstrate our ability to work in high winds or rapidly deploy or meet environmental constraints that you often have with ordinary concentrating solar power. So we'd like to find the equipment partner that needs that, the desal partner. We'd like to find vendors, people who can supply optic, insulation, mechanisms, heat exchange. And we need engineering expertise in thermal systems design and civil engineering. And that's basically, I want to go back to this just for a second to say, another unique thing we can do is, for example, we designed this thing to have the heat extracted by pulling air out and delivering hot air to a system. But we can also, if you have a tubular technology, for example, we can embed your desal tubes directly in the sand, and we can deliver together an integrated unit that is a rugged 24/7 desalination engine, all in one shipping container. And that is the end of my presentation.
Thank you, Brad. That was an interesting presentation, and you're right on time with your 4-minute allotment. Thank you for participating. Our next team captain is John Floyd, coming from Seoul MEM. They are concentrated on solar near zero liquid discharge. John, the floor is yours. Take it away.
Okay. Hey guys, can you see my screen?
Yeah, screen looks good, John.
Cool. Let's go ahead and get started then. So I'll introduce our team really quickly. First, we have Professor Qilin Li from Rice University, Dr. Gordon Zhang, Dr. Jinjin Wu, Roxy Evans, Dr. Charles Liu, and then our R&D team, Dr. Abdallah, myself, and Andrea Ibarra. So we have a bunch of expertise in business, marketing, and then a ton of expertise in desalination. So let's get into the technology. So what we do at SolMem is we use an innovative membrane distillation process termed nanophotonic enabled solar membrane distillation. And what happens with our technology is we have a membrane. The membrane is pretty much painted black. Sunlight comes down, hits the membrane, generates heat at the membrane surface, which allows for direct conversion of solar thermal energy into water vapor. And then we condense that water vapor and we get fresh water. So we call this system solar NZLD, and we have coupled this membrane distillation unit with a parabolic trough to deliver concentrated sunlight to the membrane surface, which allows us to enable a near zero liquid discharge process. So here on the right, we have an image of what solar NZLD looks like. And this technology is capable of treating brackish water, seawater, agricultural wastewater, reverse osmosis concentrate, and oil and gas produced water. So it can handle an extremely wide range of salinities. But our first focus market is going to be the high salinity oil and gas produced water. Additionally, in addition to treating high salinity wastewaters, our system can couple with reverse osmosis to make a hybrid system, which takes advantage of the low cost of reverse osmosis and the ability for our technology to, the ability for our membrane distillation technology to treat high salinity water. So our goals, we want to use the support of the Solar Desalination Prize to fast track our prototype development and meet our key performance parameter goals. And the goals that we're interested in are the levelized cost of water, which right now we have between $1.1 to $2.5 per cubic meter. With the hybrid system, that amount gets, that cost gets halved. The target water recovery, which we've seen in the lab, is up to 95%. So we'll be able to enable zero liquid discharge. We're also looking at specific water productivity, the amount of water produced per land area occupied by the treatment system, and then flux, the amount of water that moves through our membranes. And finally, we are looking to connect with partners to develop a high-performing team capable of taking solar NZLD from a prototype to a full-scale commercial solar desalination system. So for our expertise ask, we're really interested in concentrated solar power expertise and supplier connections. So if you guys have any connections with the Solar Energy and Technologies Office, I know they've done a lot of concentrated solar power competitions. That would be extremely useful for us. We also need expertise in supply chain and distribution. We need expertise in manufacturing, mass production of spiral wound membrane units. And then we need expertise in system integration, designing a, being able to take the system from a prototype to a full-scale commercial system. And we also need locations to demonstrate our technology. And if you guys are interested in our technology, which again is a direct solar thermal conversion of to freshwater vapor, you can email me, or you can also contact Roxy Evans. Thanks for your time.
Great work and excellent presentation, John. Thank you. Our last presentation, which is with Team Captain Ted Ground from Frontier Research Group. and they're working on clouds and rain optimum solar thermal desalination. Joining us from San Marcos, Texas. Ted, if you're ready, please take the floor.
Hey, Ted.
Can you see that?
Try sharing again. It didn't seem to take. Great. Yep, we can see that now, Ted.
And now this.
Yep, go ahead and pull it up full screen. Looks great. Take it away.
Clouds and rain, optimum solar thermal desalination. About our team, Frontier Research Group is named after a business of Jeff Sargent's. Bill Mancy, Ted Ground, and Jeff Sargent are business associates going back over 15 years. We each have decades of experience in water quality chemistry, aeration, thermal control, and building water recirculation systems. We have expertise in process automation technology, compressed gases, and solar heating of air and water. Jeff is a research scientist and technologist specializing in non-ferrous metals and alloys, metals analysis, sensors and analytical instruments, and systems design. I'm Ted Ground, team captain for FRG. I have an MS degree in aquatic biology from Texas State University. My thesis was on water quality in Texas freshwater reservoirs, including total dissolved solids, that's TDS or salinity. I have been lab manager for several analytical instrument labs. In the past 7 years, I've won 23 Innocentive ENEL challenges. Bill Mancy is president of Fisheries Technology Associates in Fort Collins, Colorado. Clouds and rain is a humidification dehumidification or HDH approach to desalination with an innovative combination of technologies to optimize solar desalination over a wide range of salinity. Evaporation can be greatly enhanced by increasing vapor and heat transfer rates through hot air microbubbles generated by energy efficient fluidic oscillation. Solar heated air and saline water are mixed for direct contact evaporation, or DCE. Condensation is enhanced with advanced hydrophobic materials. Markets. The 6M2 on a utility trailer demonstrates small-scale commercial feasibility. Larger designs are also commercially viable using standard shipping containers. These portable designs will be impactful in markets for desalination of produced water, irrigation, livestock, aquaculture, military use, and natural disaster response. Here are examples of our fluidic oscillator valves that we've built and of hot micro bubble generation. You notice that with fluidic oscillation, we can achieve non-coalescing microbubbles that greatly enhance evaporation. Scaling up from a utility trailer, 6M2, to shipping container sized modules, we have the solar spindle top. Our goal is an array of 25 such solar spindle tops that shall exceed 100 cubic meters per day of freshwater production. We want to push the envelope of solar thermal desalination up to and possibly beyond 30 liters per square meter of collection area per hour. Our goals are to measure oscillation frequency to optimize evaporation with air and water flow controlled by a programmable logic controller, optimize flow rates and temperatures to maximize condensate collection rates, improve composite materials to enhance condensation with analyzed photographs of water droplet formation and collection. A specific water production should exceed 5 liters per square meter of collection area per hour by January of 2022, and exceeding 30 liters per square meter per hour by January of 2023. We want to elucidate markets and end users for portable desalination systems working in collaboration with the Winston Cone Optics team in Merced, California. Expertise asked. The Frontier Research Group has entered into a mutual non-disclosure agreement, NDA, with the Winston Cone Optics team, also one of the 12 winning teams for round 2 of the Solar Desalination Prize. We will share our information and expertise and collaborate toward developing commercially successful portable solar thermal desalination systems which optimize the use of heat transfer and mass transfer technologies. For contact me. I'm Ted Graham with the Frontier Research Group. I'm the team captain. Thank you very much.
Thank you, Ted. That was a great presentation. Great to see work on portable units. They're so needed. Harrison, shall we go back to Nick?
Yes, Nick has tried to update his settings, so I'm hoping it will work this time.
Okay, Nick, the floor is yours.
No. Can you hear me now?
You sound great.
Okay, fantastic. I've dumped the AirPods and
coming up now. Yeah, just bring it up full screen.
Okay. Thank you very much, everyone. About the team, we are team D&D Manufacturing, which is headed up by Dr. Dale Polk. He's essentially been the inventor of everything from the manufacturing processes all the way through to the units that we have been commercializing to date. I have been working with Dale, or Nick Probert, I've been working with Dale for the last 7 years in the background, so to speak, in regards to capital raising and building the team, etc. And we have Aaron Allen and Don Polk as well, who are both mechanical, well, Aaron's a mechanical, but both electrical engineers working on actually the units and also the automation processes, which enables us to work in remote locations. So what is the project? Well, essentially what we do is we build everything from the ground up. We produce parabolic concentrated mirrors using composite thermoplastic composites. And then also we integrate a distillation column or a dewatering auger within the focal point. And that allows us to handle basically any input source, regardless of its concentrations, and be able to provide zero liquid discharge. So for example, we are looking as inputs, for example, working in the back end of reverse osmosis operations inland for the discharge and concentrating their brines to ZLD. We are very focused on the resource and industry and the oil and gas sectors for their processed water, oil produced water, mine tailings, waste facilities, etc. We produce obviously pure water, and then we have dried minerals, salts and tailings, which we can then reprocess at the end of the once the water's been dealt with. And finally, we deal very much with the agricultural, residential and obviously industrial effluents, where we produce pure water, and then we look to produce biosolids and even biochar, which will help increase obviously the food outputs or the fertilizer opportunities in regards to that. So what is our goals? Our goals essentially is providing vertically integrated solutions for industry, which will enable a low impact extraction of resources from waste. So tailings dams, oil produce water, industrial wastewater, effluents, etc., all need water to be dealt with. So we will remove that water, distill it, and then you have the opportunities, obviously, to produce green hydrogen, which will provide on-site energy for the operations to be able to extract the rare earth elements, the critical metals, or the low carbon ores or resources such as your biochar or biosolids. What we are looking to ask for is our research and through our customers. There is, and especially within the oil process water industry, there is VOCs mixed with the wastewater. And the part of the project is to a straightforward extension of what we want to do is incorporate multiple distillation ports and essentially be able to distill VOCs as they enter our system, and then be able to further go ahead and look at fractional distillation to create pure extraction of these VOCs for further sales, but enable us to essentially do the whole job using one system, not having to deal with the VOCs going forward. This is our contact details. We're very, very keen to discuss and enjoyed the presentations thus far. So please hit us up in the chat or via email. Thank you.
Thank you, Nick. And with that, it's a wrap on team presentations. On behalf of IDA, I'd like to tell everyone on the line and to the team captains that we are happy to promote your work. We will hopefully be presenting this recorded webinar on the IDA YouTube channel so that people who could not participate today will be able to connect with you at another time. I'd like to pass now the floor over to Daniel for closing remarks, and then we will move into the networking sessions. Daniel?